All right, let's take some time and look at vector mathematics. Vectors are a huge topic in physics. You'll see them everywhere, in pretty much every single of the modules that we're doing in all the units. Anyway, so let's take a look at what we got here, okay? Now, what a vector is, your basic definition is a quantity that is a vector is anything that has both magnitude and direction, okay? So those two pieces, magnitude, direction. And what magnitude means is that you have some sort of number. Like, for example, you see a little vector down there. It's 5 meters, okay? The magnitude bit of that is the 5, okay? It's 5 meters, and the direction, you can see that it's pointing to the right, okay? Now, if I wanted to add that to a 3-meter vector that was pointing to the right, okay, 8 meters. Not a big surprise. I could take 5 meters and I could subtract from it a 3-meter vector, okay? And lo and behold, you get a 2-meter vector. Now, notice that the size of the vector denotes its magnitude, okay? And the arrow is always pointing in the direction that it's going, okay? But this little subtraction bit is the same thing as adding this 5 meter to this 3-meter vector. Notice that that negative sign just turned that 3-meter vector around, okay? And now I've got this thing, okay? Still I end up with a 2-meter vector, but I can add 5 and 3 and get 2 with vector mathematics. But you have to pay attention to the direction. So direction is really very important when we're dealing with these things. And there are lots and lots of different quantities that can be vectors. And as we go through this physics class, you'll see examples of vectors, and then the counterpart to that is a scalar, is a number without a direction. But for example, displacement is a vector, velocity is a vector, acceleration is a vector, force is a vector. All of those things have direction. Some things that are not vectors, that we call them scalars, distance, speed, temperature is a scalar. So for example, when we talk about temperature as being a scalar, you can't have, it's not 32 degrees Fahrenheit northward. It's just right here, right now, it's 32 degrees Fahrenheit. It doesn't have a direction. Anyways, that's kind of the difference between those two things. So let's take a look. What if, and this is where vector mathematics gets kind of fun, or terrible, depending on your definition. But if I'm looking at this and I'm saying, okay, how do I add these two vectors? I've got a 5-meter vector, I have a 7-meter vector, and what do I need to do so that I can add them? I think you can clearly see that the answer is not going to end up being 12, okay? Anytime you have vectors that are on an angle, anytime ever in any problem, okay, you've got to break them down into what we call components, okay? If you look at this 5-meter vector, some of that 5 is in the x direction, okay? Same with the 7-meter vector. Some of it is in the x direction. And some of it also is in the y direction. I got a little bit going up here, and I've got a little bit going up on this one. Okay? And so we call that finding the components. Okay, I'm taking the vector and I'm breaking it into its pieces. All right? Now, how do we go about doing this? Well, we need angles. Okay? So now, these angles are not to scale. I just tossed some numbers on there. But if I'm going to finish this problem, I've got to have an angle, okay? Because the angle is going to tell me exactly how much of that vector is in the x direction and how much of that vector is in the y direction. Okay? So there's our x component. There's our y components to those vectors. Now, quick step away from that problem. We'll go back to it in just a second. Let's review some trigonometry, okay? I know it's probably been a long time since we've all kind of taken a look at this, but here I've got a basic right triangle drawn, and this all only applies to right triangles, okay? But thankfully, all the vectors that we deal with are going to live in the right triangle world. Now notice on here, normally you see this as drawn with A, B, and C on the sides, but in physics, I don't talk about A, B, and C. I've got X for the X part of the vector, the X direction, Y for the Y direction of the vector, and then R, which is the resultant, okay? And, you know, so the meaning of that word R, it's, if we look at this, if I was talking about, like, if this was a displacement vector, if I walked this far in the X and this far in the Y, the net result would be as if I traveled that distance at that angle, okay? That's where that word kind of resultant comes from. It's the result of the movement of the two components, okay? So let's step through a little bit of our trigonometry, okay? First bit of this is the Pythagorean Theorem, okay? I have x squared plus y squared is going to equal r squared. We can do a little bit of math to that to solve for the resultant. So you take the square root of the two components added together and squared, okay? And then the really fun part of this is the Sohcahtoa stuff, okay? And this is where we're looking at ratios between sides and the angles and calculating different things. But let me give you that bit of information. So stands for sine of the angle is equal to opposite. So if you look at how this is set up here. So here's my angle. Opposite of the angle is the y. Adjacent to the angle is the x. So is opposite over adjacent, or excuse me, opposite over hypotenuse. So that's going to give me y over the resultant. Cosine is adjacent over the hypotenuse. It's going to give me x over the resultant. And then last but not least is tangent or toa, which gives me the y component over the x component, okay? The tangent of the angle. Now these things are a little cumbersome to work with, so in physics we're going to take them one step further. We do a little bit of algebra, not a huge step. I'm just going to, on the first one I multiply the r's over, and then on the last one I take the inverse tangent. But now if you look over here, I've got a little set of equations that will allow me to solve for the components. I can get the y component if I take the resultant times the sine of the angle. Or I can get the x component with the resultant times the cosine of the angle. And if I need the angle, it's the inverse tangent of the y component divided by the x component, okay? Now there is one catch to all of this, and that if this is going to work with the way that I've drawn it out here. Now if you're a wizard at trigonometry, then this is not gonna be a big deal. But the way that this is written, right? X component with cosine, y component with sine. The way that it's written, the angle has to be here, coming off of the x-axis, right? The angle is touching the horizontal piece. Okay? If the angle was up here, that wouldn't work. All of these things would be switched. Okay? So we want to make sure that we have the angle in the right spot for our little equations to work. But we'll get some practice with this here in a little bit. So let's move on. Okay, so I've got my 5-meter vector, I've got my 7-meter vector. Okay? If I'm going to add them together, I have to have the components. Okay? I have the angles right there. So take a second, pause this, get your calculators out, and find the components of these vectors. Get the x component of each of them, get the y components of each of them. Okay? Now you can check your work against what I've done. Okay, so I ran the numbers into my calculator, and you need to make sure that your calculator is in degree mode. Okay, we're working with degrees right now. If you ever see a problem where they give you the angles with pi's in them, or radians, then you'd have to put your calculator into radian mode for it to work. Okay? Now, to finish this problem, okay, I've got my vectors, I have my components. Now adding the vectors is as easy as adding the components, okay? Because if you look at this, the y stuff that's already in the same direction. The x stuff is in the same direction, and so I can directly add those numbers, okay? So adding those numbers directly together gives me these figures, okay? And notice I've taken these little triangles, and it's like I'm adding the triangles together, and now I'm building a brand new big triangle. So I've got a y component, I have an x component. How do I go back to the resultant? Well, Pythagorean theorem, right? Use the Pythagorean theorem, and that'll give you the resultant. And then the last piece of this we need is what's the new angle? So I take the inverse tangent of the y piece over the x piece, and that gives me my new angle, okay? Every single vector problem works this way. It all boils down to the exact same thing. Find your components, add the components, Pythagorean theorem, inverse tangent, okay? Or sometimes you have to go backwards, or it'll give you the resultant and the angle, and then you go back, okay? So, another quick practice problem. Again, you can pause this and work through this. You've got a 10-meter vector, a 3-meter vector, and a 12-meter vector, and they're all at different angles, okay? So see if you can work through this, and then I'll show you how I went through and solved it. Okay, here we go. So, first step, find your components. I'm going to get my calculator out, and I'm going to find the components. Notice on that first one, that thing is just an x component. It has nothing in the y direction. So that makes it really easy for me. Okay, now, one really quick thing to notice, if you look at that x component on the blue vector, it's negative because it's to the left, okay? It's if you notice, all the y components are positive because they all point up, except for the 0 one. But the blue vector, you have to put that negative there because it's to the left, okay? So now let's combine all of our numbers. And you can see there I'm going to build a new triangle. Okay, and it's got just a little teeny bit in the x direction, quite a bit left in the y direction. So looking at that, I'm going to guess it'll have a pretty steep angle. Okay, the resultant is 5.25. And my inverse tangent gives me my angle of 84.19 degrees. That's almost straight up and down. Okay. Last little example here. Now, if you look at this, and I ask you to find the components, if you use, if you take 15 times the cosine of 51 to try and find the x component, it's not going to work for you. Okay, if you notice, my angle right now is touching the y-axis. So the cosine thing isn't going to give you the x. I need the angle to be here. If I'm going to use my little degree tricks, I've got to get that angle. Okay? And that's easy, right? This whole thing is 90. So 90 minus 51 is going to give me 39. Okay? And then I can use 39 and find all of my components. Okay? And so there's a little bit on vector mathematics. All vectors work the same. It doesn't matter if it's a distance vector or a force vector or a velocity vector. Find the components, use your trigonometry to combine the vectors. Now, I guess the one catch here is, can I add a distance or a displacement vector to a velocity vector? No, right? You can't do that. They're not the same. They have to be the same type of vector. So, there you go. There's a couple of examples of how to work with vectors and a little bit of trigonometry in there. Again, if you have any other questions, email me, let me know, and I will help you through those problems. And good luck on your guys' homework this week.